All right, so in this last lecture for Chapter 1, I want to give you some more information and examples about isotopes and ions of various elements. The first question I want to address is something I kind of alluded to briefly a few lectures ago. Why aren't the atomic masses on the periodic table whole numbers? Okay, this is a very interesting question. Just to remind you guys, if I go back to the periodic table, which I introduced a few lectures ago, if you look at any of the top numbers here, they go out pretty far in number of decimal places. And that's really a contrast from the atomic numbers, which are always whole numbers. So if the atomic masses are supposed to be just the addition of the number of protons and the number of neutrons, why aren't they whole numbers? You can't have half a proton. You can't have half a neutron. So why are those top numbers, the atomic masses on the periodic table, whole numbers? So I suggest that you pause and think about that on your own for a moment. The reason is that in nature, elements occur as mixtures of isotopes. So elements occur naturally as different isotopes. I guess I don't need to say naturally again. But in nature, elements occur as different isotopes, kind of like the different colors of this ink. So let me give you an example. In nature, bromine occurs naturally as either 79 bromine or 81 bromine. So there's a lighter isotope, 79, and a heavier one, 81. The lighter isotope constitutes 51% of all bromine atoms in nature. The heavier isotope makes up the remaining 49% of bromine atoms, with the exception of some other trace isotopes. If we look at the periodic table, let's check out the atomic mass of bromine. Okay, so bromine is all the way over here, and we can see that its atomic mass is 79.904. Definitely not a whole number, but between 79 and 81, closer to 80 than either of those two numbers. So effectively, the atomic mass on the periodic table of all bromine atoms is 79.9. And that reflects a weighted average of the naturally occurring isotopes, kind of weighted according to their natural abundance. This number is closer to 79 than it is to 81, simply because slightly more of the total natural abundance belongs to that lighter isotope. However, the number is almost dead in between because we have approximately 50-50 ratio between the heavy and the light isotope here. So this is not only true for bromine, it's true for all elements that the atomic mass on the periodic table is a weighted average. And it's a weighted average of the masses of the isotopes, kind of weighted by their relative abundance in nature. Okay, so that's true for bromine, as we just saw. It's true for all the other elements as well. So we were using atomic symbols to figure out the number of protons, neutrons, and electrons in various isotopes. Now I want to define another vocabulary word that begins with I, ions. So ions are just charged species. They are charged atoms. They can also be molecules. When you have a charged molecule instead of an atom, you would call that a polyion, and we'll learn about that in a subsequent chapter. The charge arises from the gain or loss of electrons. That is very important. The charge arises from the gain or loss of electrons relative to the fixed number of protons in the nucleus. Now, what do I mean by that? Well, think about where the protons are. They're locked away in the nucleus in the middle of the atom. Protons are zipping around in the extranuclear space, and it's relatively easy to pluck off an electron. It's much more difficult to change the nuclear composition. So protons are pretty immutable, except in nuclear chemistry. But electrons, especially the outermost electrons, which we call valence electrons, those can be easily gained or lost. And if you lose an electron relative to the fixed number of protons, then you are going to create a positively charged ion. If you gain an electron relative to a fixed number of protons, you're going to create a negatively charged ion. So, kind of saying that again, when electrons are added to or removed from an atom, you get either a negative ion, which is called an anion, or a cation. Now, an anion is just a negatively charged ion. So any particle with a negative charge is called an anion, and a cation is a positively charged ion. So anything with a positive charge is called a cation. And you indicate the charge with the right superscript. So let me give you an example. Oxygen can easily gain 2 electrons to make the O2 minus anion. Now, oxygen is number 8 on the periodic table, and it has an atomic mass of 16. So can you tell me how many protons, how many neutrons, and how many electrons are in this ion of oxygen? Okay, well, we can use the same tools we had from before to figure out the number of protons and neutrons. The number of protons for oxygen is always going to be 8 because that's its atomic number, the bottom number. The number of neutrons is going to be the top number minus the bottom number, which also gives us 8, coincidentally. Now, the number of electrons. If this were a neutral atom, we would have 8 electrons to balance out the 8 protons, right? But it's not neutral. It has a charge of 2 minus. That means that it has gained 2 electrons relative to the fixed number of protons. So the number of electrons must be 10 to account for the 2 minus charge. On this ion. Let me give you another example with a cation this time. Let's consider 5525 manganese 6+. How many protons, how many neutrons, And how many electrons are in this ion of manganese? Okay, well, we just have the atomic number, 25 protons. 55 minus 25 gives us 30 neutrons. Now, how about the electrons here? A neutral atom of manganese would have 25 electrons. But we have a charge here of 6 plus on this ion. So that means that we must have lost 6 electrons. So we're going to be left with only 19 electrons relative to the 25 protons in the nucleus. That gives this manganese ion an overall charge of 6 plus. This concludes our discussion of the Chapter 1 material.